we are currently on week 13, so that's over here. So for today, this week, my plan for you for this week class is to do a overall review of entire instructor that I have provided for this power methodology class, right? So today's job is to go over a comprehensive review. There will be extensive note writing, so if you have your pad, I see some of you already have your tablet, or if you have a ready notebook, that's great. So I'm going to kind of summarize all of those instructions I have talked about, and these information will definitely be on your final exam. So we do have a final exam on week 16. I don't know if you can see that. So that's 3 weeks later. The final exam is a comprehensive exam. You can bring your notebooks. You're allowed to bring an electronic dictionary and a engineering calculator. So that's the two things you can do. Now the week before that, week 15, we have Dr. Shi. He's also invited to talk about powder analysis or particle size analysis. So again, he's from Melbourne Analytical. I don't know if you recall, I think a few weeks ago, a long time ago, we invited Dr. Lee. He's also from Melbourne Analytical to talk about XRP, right? So there's another scientist that works for this company who will talk about particle size analysis. So week 15 is actually the week where our term paper is due. So remember that this is the week you have to submit. So next week we won't have class, and the only reason why I didn't have class is I'm having this week for you to take some time to finish your term papers. So no excuse. All right, so make sure you submit on time. So this term paper, one thing I noticed when I haven't submitted the outline for you guys that have submitted. One thing I noticed for all of you that have a constant kind of a mistake or error is that being consistent. So make sure that for your term papers, make sure you're very consistent for each of the stuff you write. Make sure you follow the template. One of the ways that I check if I'm being consistent is normally I print out the documents. You really print the document out and you can check it very thoroughly. Something that doesn't make sense. Okay, so make sure the term paper follow the guideline. If you don't follow the guideline, you will be heavily being penalty for these scores. So the term paper overall, these approximately takes about so I think I have the so if you see the total amount is, if you add all these up, it's take about 70%. So the remaining comprehensive exam is take about 30% of the total grade. Okay, so make sure you follow all these guidelines. Okay, so any other questions? Good? All right, so if you don't have any questions, let's jump into note-taking. So I'm going to talk about powder formation. I believe last week and the continuous few weeks ago, Professor, I think Professor Cho, Dr. Cho has extensive talk about powder injection molding. So while giving you some applications, I felt that it's good that we kind of do some summarize. So if you have your notes ready, you're going to take some notes. All right, so powder formation, we're particularly going to talk about, you see this? I'm going to zoom in this talk about atomization. Okay, so ATOMIZation. Can you see that? Okay, so what is atomization? So a few things I'm going to talk about is the breakup of a liquid metal into fine droplets. So typically, it's smaller than 150 micrograms. The way powder was being formed from carbonization is forcing or molten through a small orifice and breaking up the stream by a powerful jets of compressed gas or water. Right? So, on the basis of the polymerization media, so what I mean for that is there's two ways through accommodations that you can get your powder. So, the polymerization media. It's either through gas or through water. This is a typical way you can get. Now, on the basis of kind of energy, so kind of a basis of energy, you can either do it from centrifuge. It's a very common way you see if you go to a powder fabrication laboratory, centrifuge, or through vacuum. There's also another alternative route, and through plasma. This is seldom seen, but it's also being done, and lastly, ultrasound. Okay. Before we cut it off. Okay, good. Okay. So I'm gonna okay. So during the caramelization process, there's 4 stages. 有4个阶段，就是你在制造借由 caramelization 的方式有4个阶段。There's 4 stages. So 4 stage or forming caramelization powder, 4 stages. The first stage is the impingement of high velocity jets of water or gas being produced sinusoid wave, which cause disturbance in the liquid water, in the liquid sheet. So this is the first stage. Go ahead and mark that.
second stage is you have a wave fragment. Ligaments formation through shear force. Is produced by the disturbance at stage 1. Right? So can you see my handwriting? Be clear? Yeah, so wave fragments and ligament formation through shearing force is produced by the disturbance at stage 1. Alright? So, third stage. So again, this is 4 stage. So, third stage is you have a breakdown of ligaments into droplets. Okay? So here comes the interesting part. If you want to get a regular particle shape. What you do is you have a high surface tension and low cooling rate. Okay? And if you want to have, instead, if you want to have a regular particle shape, you have a low surface tension, but a high cooling. Alright, does that make sense? So this is the third stage. So if you want to have a regular particle size and regular particle size, that's the difference, right? The regular irregular particle size have high surface tension, low cooling rate. Irregular, then you have low surface tension, high cooling rate. Alright? So moving forward, the fourth stage. So what does fourth stage? You have forward deformation and sheen of droplets and wave fragments into smaller particles. Alright? So these are the forming process where you obtain through atomisation of your particles. Alright? Any questions so far? Okay, so if you're still copying, that's okay. Later on, I'm going to post this notes on Moodle as well. Or if you want to take some time to digest, we're totally fine to take photos right now. So that rather to wait for me to upload on Moodle, you can take photo right now so that you will have the notes by yourself. Or simply, if you're really so lazy, you can just come, I have the notes over here, you can also take my notes over here, that's fine, okay? Either way, as long as you get all the necessary information, I'm very open-minded for that. Okay? So, with that, I'm gonna continue to push on, all right? I'm gonna put a few notes I wanna kind of cover. Again, like today's thing is you might think that's kind of jumping back and forth, but it's really rather a summary or comprehensive of all the lecture instructor that I've invited, all right? So don't get stressful without jumping around. All right, so I'm gonna move forward, okay? So microscopy, SEM. SEM stands for scanning electron microscopy or microscopies. I'm sure that for those that have material background, I'm aware that you want to know how to use these technologies. However, there's a few science things I feel worth spending some time to have a discussion. Right? So how do a microscopy do functions and what sort of information we're getting? First is that definitely you will have. So first thing is you definitely have a subject, right? So you can imagine this is a subject. So with that, you have what you so-called a incident beam, right? Your energy or something you shoot into an incident beam, electron beam, right? So when you shoot onto a substrate, there is a lot of information you will get. So the first information is that you're going to get a secondary electron. That's the information or the information we're looking at to get our SEM images. Of course, you can also use the backscatter to get that image as well. So that's the backscatter electron. And of course, you have these X-ray going on, so this is the X-ray. And you have the OJ, which is that energy is really weak. All right. So somehow, if you're able to penetrate with the instant beam, once you penetrate, what we call that is transmitted electron, right? So then that moving forward will be called TEM, right? Now there's also a few information we can obtain. One is what we so-called inelastic scatter. Again, this is really depending on your subject. So you definitely get also this information and elastic scatter. Alright, so these are the information to review when you conduct with SEM on your sample, right? So one of the things I think is, for me, it's really useful information, and particularly for you when you use SEM, is often you need to recognize is when you do EDS. I'm sure everybody in this room has done EDS in one way or another, right? And you need to be cognizant about what's the depth, the penetration of EDS can do, right? Because you're getting somewhat a semi-quantitative analysis of EDS, right? So I'm going to do another drawing, sort of a schematic to help you, remember these information. So again, think about if you're having now I'm trying to zoom in, you have a condensed electron beam or a concentrated electron beam. So you can think about that as your SEM beam. So this energy typically are 5 to 50 keV, right? And it's shooting down to your substrate, right? right? So over here, of course, I'm drawing this because there's no information. And I'll do this in a way that's making more sense. So in this region over here, is what we so-called OJ detection, OJ electrons. So that's about 1 nanometer depth if we want to obtain that information. So that energy is roughly 10 to 100 eV, okay? And then if we move a little bit farther beyond over here, this information over here is what we so-called the secondary electrons. So the penetration depth for this is about 100 nanometer, and the energy is about 1 to 10 eV. All right. So if we move a little bit farther beyond, I'm typically drawing this like this. This area is what we so-called backscattering electron, 非常生成 backscattering electron. So this penetration depth is about 1 micrometer, and this energy typically around 10 keV. Good. And then if we continue to move a little bit forward along the path, this area is what we so-called the characteristic X-ray. And this is roughly again 10 micrometers. All right? And then below here is what we call continuum X-ray. So again, just X-ray is roughly same 10 micrometers. Now, this information that I have not around this area is what we so-called the fluorescent X-ray. So it's less interest. Mostly we don't really care, but depending on your research. So this again is also 10 micro. Right. So either way, I think in some way you'll do SCM, right? So I think a couple of few information is for your benefit to remember. Two information. One is the secondary electron. The penetration depth, as I wrote, is about 100 nanometer, right? And the backscattering electron is about 1 micrometer, right? And the characteristic X-ray is about 10 micrometers, right? So this is where you're getting your EES is coming from, right? The typical EES information that you can obtain is roughly depth about 10 micrometers. You can't go beyond that, right? So if you have surface and if you do an EES, likely if you have a more in-depth coding beyond that, it's difficult to detect any elements. All right. I think the bell just ring. What I'm going to do is I'm going to continue forward to my lectures, and if you want to use the restrooms and any stuff, anyways, please feel free to just use it. My plan for today is just continue to provide all the notes until I'm done. Okay, so feel free to take a break if you need by yourself. All right. All right. So any questions so far? I believe this semester is a class that's offered on is it an instrumental machine or electric experimental analysis? Was this information ever provided? 你们那个很低声的有上过这个方面的课程吗？你们没有？你们有吗？不知道，知道吗？不知道，没有。周老师有上周老师的课吗？周正全老师没有。OK。So, let's continue moving forward. Alright, so hotness is another thing that's constantly mentioned. So, I think sometimes these are elementary stuff, consider your graduate level, but the reason why I mention it is, what is the definition of hotness, by the way? Yeah, I don't know. Except for my mom, I think he's going to answer, but I want to ask student that's taking this class. Who can give me the definition of hotness? 谁给我那个印度的定义？有没有人知道？讲错都没关系。学敏，你知道印度是定义是什么？强度一种，好 ，OK， 你大概不到表面，但是没关系。好，还有没有其他的再更具体的？怎么样？good， 很好，标准答案，就是材料在塑性变形，它要给你就是 the number for this。What the student does convey is the information that provide a minimum number for the material plastic to hold, right? So the higher the number, meaning that the material is more difficult to reach plastic information. All right, so this is information. It's a very important information that you have to remember because unlike when you have to do your tensile tests, bending tests, these specimens that you make, you require to fabricate it, right? However, by doing hotness, it's faster because you then don't have to make a specimen, but you then know the yield strength for these specimens, alright? Does that make sense, you guys? So, what is the definition of hotness? I'm gonna again copy this down for you. Is the material resistance to localize plastic deformation. Alright? Super important. I think you should really be more remember this when you see hotness. This is the definition you should remember. There is a lot of hotness. There is the new hotness. There is the Baker hotness. One thing to recognize this is that each of these hotness that you measure, oftentimes it's difficult to compare within each other. For example, if you do Baker hotness, and one of your colleagues decided you do new hotness, of course there's the table where you can transfer, but I don't really recommend that. So just again, like when you do the material, for example, if you do Baker hotness and you decided to do say 100 gram of load, I suggest you be consistent for all your specimens so that you can have a relative compare. Now, for those that do ceramic materials, oftentimes when you do Baker, like the Baker hotness, you get this like dimple, right? And you might ask, hey, professor, how about we do 100 gram or 100? How about usually it's measured like this? They don't give a gram. They just point one means 100 gram. Okay. 0.5 meaning 500 gram, and you say HB1 is 1 kg, right? And say you do this harvest on the specimens, you might ask, hey professor, which of those should I use? One of the things or attributes you see from a specimen is that you see these kind of things going on. So if you have already potential cracks that's being propagated, I suggest you decrease your load. So these are cracks that you want to avoid because these cracks actually influence your detections, right? So if somehow you use this load, you get this crack, right? And reduce it to HB 0.1 and see if you still see these, all right? Does that make sense? Okay, good. So moving forward, we're gonna swap to polymer science. I'm sure since we're in mechanical engineering, all we care is metals and maybe a little bit about ceramics and mechanics and all this stuff, right? But since we're in powder metallurgies and metal injection molding, there are some polymer stuff that we are included, right? So what is polymer science? A few things. I'm sure you know the difference between thermoplastic and thermoset, right? So can anybody give me a definition of the difference between thermoplastic and thermoset? Anybody? Renan, do you want to volunteer about the difference between thermoplastic and thermoset?
Thermoplastics are just living by heat. You can go into the somewhere state and then by doing you can back to its state. But thermosets are once it means by application of heat it will be provided some shape, so it will take that shape for longer time. If again heating it will burn.
Yeah, I think so. Roughly about 85 to 90% correct. There's a couple of few terminologies that it will be wonderful if we would also include, such as cross-link and curing. So these are the kind of terminology usually we use in polymer science. For thermoset, a great example of thermoset, I'm sure you do aware of epoxy, right? And say the resin printer we do resins, these are irreversible. So they cannot be heated up and then do a molten form, liquid form. Again, you have to remember this is thermoset. So thermoplastic, what is that? Thermoplastic meaning like for PP, PVC, PE, those thermoplastic material where you can draw the molecular structures. 它的分子构造 for those, the molecular structure, meaning that they are reversible, right? So, so today we're going to first talk about what is the thermoplastic material, because these are the most interesting. So, thermoplastic. Alright, so thermoplastic, according to the categorizer thermoplastic, then we categorize into amorphous and semi-crystalline, right? So, there's the amorphous material, and of course, there is the semi-crystalline. So what are the materials that are amorphous? For example, PVC, PC, PMMA, and ABS, PS. These are amorphous materials. Semi-crystalline, for example, PE, HD, HD means high density polyethylene, and again, you can see LDPE, low density polyethylene, and then you have PP, PT, POM, PTFE, and PA6 or PA66. So PA6 over here means nylon. Nylon, right? So nylon, by the way, is a trademark that is being registered by DuPont, right? So normally in a more academic world, when we say nylon, we say polyamide. So it's PA6 or PA66, all right? Or there's also PA12. So these are crystalline. Now, few things to kind of recognize. When I say HD, high density polyethylene, and low density polyethylene, if commonly it's known to recognize that HDPE has more crystallinity compared to low density polyethylene. All right, this is the way when I say HD, what that actually means. All right, so there's a lot of confusion between amorphous and semi-crystalline. By the way, Quan was to get a fully crystalline material is really difficult. Mostly when I say semi-crystalline, please do not get kind of confused. Semi doesn't mean 50%. It's actually relative low. It's about 5 or 10% of crystallinity. 所以当我讲 semi-crystalline 就半结晶，其实不是这个其实它的结晶量大概只有5%、10%，就已经非常多。So mostly when we deal with polymer materials, mostly they are amorphous. 也就是非结晶 right? Another non-academic way to determine if it's not semi-crystalline but amorphous is to see if it's transparent or not. This is not a very academic way, but you can definitely recognize a lot of amorphousness. Like for example, PC, PVC mostly transparent. Right? Sometimes it's not because they add fillers inside, or maybe color pigments inside, so that's a little bit easy. All right, so let's talk about. So we're gonna go ahead and draw an XYZ axis. I'm sure in some way in the past we've been doing undergrad, we do polymer science. If you haven't, that's okay. You have seen this proof. So what I'm going to plot right now is plot the y-axis as specific value. Specific value, and then over here is going to be the temperature. Okay, so y 轴是体积比，然后 x 轴是 T。So what's the difference between specific value and value? 体积跟那个 specific value. 这个我不知道。What's the difference between specific value and value? Anybody knows? I'm sure. So FYI, there's also specific mass, specific density, specific value. Anybody want to share? But Tyler, do you have any thoughts about this? When I say specific, what does it mean? Special?
Specific value is like the value is like the value is defined by the value defined by the grade or area.
Yeah. So one quick sentence is just to consider gravity, right? So divided by G, right? Gravity, right? So when people talk about specific density, specific value, it's meaning that they consider gravity. That's it. Divided by G, all right? So 9.8, right? So it's just gravity. That's it. All right. So sometimes you can consider its specific value is value because we're on Earth. So if today we're on Mars, Moon, the specific value is different. Right? Does it make sense to you? So we're on Earth, right? So 9.8. So then we draw the temperature, right? So from room temperature to all the way to mountain temperature, right? So if I were to ask you, hey, how about you draw these material curves, the amorphous curve, you draw the amorphous curve and the semi-crystalline, and crystalline, 结晶的 material. What will we look like? So let's identify a few lines. So this is TG and TM, right? So this is glass transition temperature, and then this is the melting temperature, right? So I'm sure that in some way you heard of glass transition temperature, 40 to 1, okay? TM is the melting temperature. So if I were to ask you, hey, can you draw the amorphous material on this graph with a plot or y function is specific value and T is the temperature of all three material? Can you draw that curve out for me? Man, during my master's degree, I could do during my defense, I was asked by a professor to draw this curve on the blackboard. So again, sometimes you have to say that in order to do a defense, what does it have to give you a tough time asking some fundamental science? Right? Yeah. So life it is tough, all right? So if you decided to do academic, be ready, right? So this is this you should know. Doesn't make an excuse to say that you don't know. Right, so let's do the easy part for crystalline materials. The curve normally is, so this is red and green and purple. Right, so red, you have a curve like this, right, and then it melts. Like that, right? Now, for amorphous materials, it will have a TG, right? So for amorphous material, like this. And for semi-crystalline, so this line is the amorphous and semi-crystalline and crystalline. So crystalline, as we all understand, it has a melting point, right? It's no debate for that. Semi-crystalline, which is the regime between amorphous and crystalline, so you will have glass extrusion temperature and melting temperature, right? So when you draw the curve, it is over here. This is let me make this curve a little bit better. It's not this. So over here, there's a slightly curve, and then there's a melting that goes up. Amorphous only have TG point, so over here you have a slightly value change, but you don't have a melting point. All right. So there's no melting point for amorphous. So think about epoxy, for example. It doesn't have a melting point. All it does is it turns into carbon. Right. There's no melting point. Imagine you have a solid that turns into a liquid. Right. There's a transformation going on if you know your thermodynamic. So there's no turning point for amorphous. All right? So these are the basic curves you should recognize. All right, so another few things I want to continue to talk about is, so what is glass transition temperature? Just to review before you. So a few things, if you somehow you don't have a DSC to get your TGA, no. If you don't have a DSC to get your TG, the quickest way is to know its melting point. So normally, not normally, but the rule of thumb is about 2/3 of your melting temperature. That normally is your TG point. Okay, so TG point, if you review your thermodynamic material, it's a second order. We won't divide that equation. The melting point basically is first order. Alright? So what is glass transition temperature? So anybody want to volunteer to give me the definition of glass transition temperature? 玻璃转换温度，玻璃转移温度，它的定义是什么？大家有概念？那么后面的你们有没有去？ 知道吗？知道。没有，用那个最很白痴的说法都可以，就是最很不学。Any definition is a good definition to remember. Anybody wanna share? Anybody? What is glass usually? 是玻璃转，有没有？
开始接近的温度。
开始结晶的温度。好像不是，因为它没有结晶。OK， 你再翻一下你电脑。我回来马上当场暴毙。但是谢谢啊，还是有。Alright, good. Anybody wanna share ideas? 强强你们知道吗？强强你知道吗？来 Google 一下，那个 OK，Google is fine。Has a 叶是有上到这个吗？没有上。对。
玻璃态转向胶态的一个，就是它有3个状态，然后就是玻璃态转橡胶态，然后橡胶态再转到另外一个气态，它们这种
叫玻璃？
玻璃态就是它还是玻璃的时候。
什么叫玻璃？ Yeah, no, so that's a good thing. Yeah, sometimes it's always good to review the definition. Right? When I was a PhD student, I suffer a lot because often I get asked definition all the time. What is this? Right? So what exactly is glass? Do you have an idea what is glass? What is glass?
glass
Yeah.
晶石嘛，就是晶石态，就是里面是有结晶状态，然后
Yeah,
转
that's
成
crystalline, right? That's not glass. 基质就 crystalline. No. Yeah. Okay. So let me give you the definitions. So passage emission is the temperature. Range. With on substrate change from a rigid classic to a solid. And is usually measured in terms of the stiffness or modulus. Right? So, what does that mean is if I were to draw a graph like this, the y-axis is the log function of E. The axis is again temperature. So if it's so for example, if it's again like a thermal set material which has a TG point, what you see is you're going to see a curve like this. Right. Now, if it's a thermoplastic and it's a semi-crystalline or crystalline material, what you see is come over here, it will drop down. So over here, this is the melting point. The melt, right? This region over here is the TG point. Alright, so within this region normally, we say that it's a TG point. Okay? So this curve is the zone So I also will give you some quick kind of a summary of what's going on. So what this graph right now I'm doing is I'm kind of throwing you two materials, the thermoset and the thermoplastic, right? So as I explained thermoset, all the thermoset are basically amorphous, all right? So that's why at the beginning I first talked about thermoplastic. In thermoplastic, there is amorphous and semi-crystalline. However, in thermoset, it's all amorphous. So when we deal with amorphous, there is no melting point, all right? So think about epoxy, all right? So under this curve right now, meaning that there's no melting temperature for that, meaning that this curve is continue on. Now, for thermoplastic, if we're talking about semi-crystalline materials, then there is a melting point. This curve goes down, all right? So the modules change, all right? Does that make sense? So when I talk about, this is the definition of glass transition temperatures, there's many ways. First is you start with the glassy state. Once you pass the DG point, you basically turn into a rubbery state. If you continue to heat up, eventually it will form like a watery, or what we so-called model technology is water flow, and eventually it melt into like a liquid form, right? Does that make sense to you guys? Right? So the catch, I think the information I want to convey for this slide is that if someone comes to you of a particularly polymer materials, first you need to ask, is this thermoplastic or thermoset? I think this is understandable, right? Second is if it's a thermoplastic, the follow-up question is this amorphous or semi-crystalline? All right? Because if it's semi-crystalline, right, meaning that right, there's a TG point and then there's the melting point, right? If it's amorphous, there's no melting point for that. All it does is change the carbon. Okay? All right, so any questions so far? All right, so if we don't, let's go ahead and move on. So bending test. So I'm gonna spend a little bit of time to talk about bending. Again, the reason why I talk about bending is, I don't know if you recall it, we spent some time to talk about statistic, and when we talk about statistic, often it involves Weibull statistic, right? So important thing to remember for that is, why do we use Weibull statistic, right? In this kind of, well, here in this summary I won't talk about because we already spent some time on it, but for your final exam, I will ask you what is Weibull statistic, why are we using Weibull statistic, why. So do review your notes. Why are we using Weibull statistic? Right? That's the question I'm going to ask you for final exam. Oftentimes when you use Weibull statistic is, I think a lot of people will combine with bending test, right? 4-point bending is a very common thing, or 3-point bending. Again, you can use other mechanical testing to do your Weibull statistic, but bending test is just widely being done that combined with Weibull statistic, all right? So the question then comes into, when I talk about bending, by the way, this is a cool question. So why do we do bending instead of, why can't we just do tensile test? Why do we insist on bending for some material? 为什么可以做拉伸不做拉伸，我非得需要做弯曲测试？ So just a quick question. So why can't I just do tensile tests instead? Why do some material need to do bending?
就是它材料表面的测它这个表面的张力力跟压力力之间的关系。
你可以知道的，但是就为什么材料有些需要去做弯曲测试，我们不去做为什么拉力测试不会是个很好的选项？
因为拉力测试是直的，然后它是会产生紧缩。但是你如果是弯曲测试，它是变成是你降压，然后这边是产生压力力，这边是张力。
对啊，有一个 compression and tension 嘛。对啊，但是就是有些材料为什么它很适合去做弯曲，但是它做拉力其实是不是很好？比如说我再更进一步，我让大家，等下大家知道为什么吗？不知道，我知道确定，然后我可能再给你一点答案，然后再看看可以知道，就是像陶瓷，为什么我们做拉力不是做弯曲？
因为它太脆了，没有太
说不知道为什么吗？啊？ OK， 韧性，然后比较更专有一点，为什么？后面有人知道吗？为什么要做弯曲？韧性是一个答案。Do you guys know? Alright, so let me get back. So let me get back to why do some materials have to do bending tests instead of tensile tests instead? So it's because the K1C is really low. OK， 所以韧性就破坏韧性它太低。你试想想看，你刚才有想到已经 touch 到，就是说，你今天把这个玻璃的饰片，你想想看 ，think about if you, do they have a glass sample, right? And if you try to roll on a low frame, right, a loading frame, right? I can guarantee you that way before you start doing a tensile test, it already fractured, right? 你有一个玻璃饰片，如果你放在一个拉力上面夹住，它早就破坏了。So I think why they sometimes when we do ceramic materials, it's just a habit when we do bending. It's not because we can't. Of course, you can do tensile. It's just because the K1C 就是它的破坏韧性 K 是太低 Okay. All right. So this is important information you can get. So I'm spending some time to talk about bending. So this is we're talking about that. 所以静态。So there's the 3-point bending and 4-point bending, right? So when to use which one? So 3-point bending, mostly the material homogenized, right? Homogenized material. Homogenized. And 4-point bending is non-homogenized. So normally when you see 3-point bending, you have a concentrated load. Right, you have a concentrated load. And this 4-point bending is you have a larger region to do your 4-point bending. So this is to avoid premature failure. So this is important. Alright, so in case you have no idea what I'm talking about, is when I talk about 3-point bending, is something like this, right? You have your specimens like that, and then you have a support on either end, right? And then you have a load pressing like that. We will call that as F. Force, right? I'm sure for those that are mechanical background, you do know how to do your bending moment, right? So the bending moment is you draw a curve like that, right? And then you also have curve like this, right? Does that make sense? So the bending moments, right? So again, these details I won't dive in, but one of the important equations you should remember is the stress, the maximum fracture stress is 3FL divided by 2WH squared. So what that means is that this is the H, is the height. This is the height. This is the H. This is L. So if it's half, meaning that's half of L. Alright, so force you already know, L is the length of here, the width is the width that's going inside, right? The width, the H is the thickness, right? The height. Okay, so what this equation gave you is, supposedly today you have a specimen, right? And if you do a 3-point bending,
3点弯曲，然后那个机器应该会给你的最大的力量值，就断掉的话不是会有值嘛，对不对？最大的那个值。Once you have that load, what you do is you put that in this equation. If you're doing 3-point bending, right? You put the load, you measure the length, 你试遍的长度 ，W 就是你的这个宽度 ，H 就是你的厚度 ，Pa 就是它的 stress， 这个 stress 就是它的 ultimate 就是 strength，ultimate tensile strength。Okay? 所以 when we normally talk about ceramic materials, when we say about strength, it's equivalent of yield strength and ultimate tensile strength. Okay? 所以 when I ask you to draw a ceramic stress plate, what you see is it's always like this. Right? 这个值就是 yield stress 也是 UTS 都是一样的，它没有过什么相对什么，它是同一个值。Okay 吗 ？It's the same, right? So you will have the force you apply to get the stress factor, right? Is that easy enough? Do you understand, you guys? Now, there's another few things. Unfortunately, for ceramic materials, normally we don't use 3-point bending. We use 4-point bending. All right. So, what other condition will we use 3-point bending? Right. Perhaps it's metal. Right? Metals you can do 3-point bending. So, normally for ceramic materials, again, the same specimen, the same length. What you do is instead you have a load like this on this end. So normally the load applied with you is a little bit smaller compared to the supporting end. Alright? For these supporting and the applied force, these dimensions are specifically regulated by either the ASTM standard or ISO standards. Alright? So remember these are heavily regulated. I don't know the numbers, ASTM or ISO, right? So these dimensions 这些的精度，这些都已经有详细的规范，不是说你去调怎么样的状况。所以 this is half of the force, half, okay? All right. So again, you draw a lot of again the bendings and all the stuff. I'm gonna again just give you the equation. So this is the maximum is F.L divided by 2WH squared. Alright? So this is 3-point. This is 4-point. Alright. So how I think is your take home homework, right? So homework that you take home to do, how do I get this value? FL divided by 2WH squared. For 4-point bending, 3-point bending, 3FL 2WH squared. How do I get this number? 所以你们回家功课自己去算一下，大概以你们现在大概花半天时间到1天时间，所以你觉得值不值得？如果你研究有牵扯到你要做这个机械测试，我就建议你花一点时间去了解一下。Alright. Alright, so this is a 4-point bending and 3-point bending. Alright, so the question then comes into the bending modulus. So when you sometimes look at the technical data sheet, 就是一些技术资料的时候，他们会 sometimes they will provide. So this over here, you get the modulus as well. So the modulus, I didn't really give you. You can also use these values to calculate the modulus. 就是那个杨氏模数，你可以借由这个值去算出来，我只是没有给你。如果你去复习你的材料力学，都可以算出来。So this modulus that you get, the bending modulus you get, is not the same as the tensile modulus. Right? So I want to say is the tensile modulus is not the same as the bending modulus. Right? That's not the same, right? It's completely different modulus. Okay? So if you have enough specimen, what you could do is actually you can do a plot like this. This is E is the modulus, and normally it's GPA. The
axis over here is L divided by D is span to depth ratio. So this is the A ratio. So L divided by D. So by the way, the D over here, actually, sorry, let me correct this. The D over here is the H. Okay? So what you see is if you do tensor tests, this is the tensor modulus. 就是那个拉伸的那个魔术，不管你今天适配的大小，它永远那个魔术都是一定值。但是如果你今天做弯曲的话，它会不一样。So if today if you do tensor modulus is going to consistent, regardless of the span to depth ratio, right? However, if you do bending, it's going to be different. So a great example of him is going to provide you the answer for that is you will see something very similar like this. So this is 116 ratio, 132, 1 to 40, and 1 to 60. And then eventually you will see a curve that closely match up with tensor modulus. Okay? 所以就是这个 span to depth ratio. So 1 to 60 meaning that today your specimen is very wide, very long. Okay? And 1 to 60 meaning that it's very small. Right? 那很小的。那 why is there why you see there's a big difference over here when we increase the span to depth ratio? What happened is because these values, when it's very small, 1 to 60, 1 to 32, is because due to the shear, these specimens are so small, there's shear thing going on. 有剪切力所造成的，所以它的so these bending modulus that you obtain is roughly smaller than the tensor modulus. So today, if your professor asks you, hey, I want to have a modulus, right? And you're just too lazy that you don't want to do a tensor at the same time, but you want to do flexions, then I strongly suggest you to consider making this span increase long enough so that there's no shear phenomenon, playing around, right? So if the span ratio is long enough, the bending modulus, tensor modulus are approximately the same, all right? Does that make sense to you guys? 这有没有对你们有没有帮助 Alright, does that help? Hopefully that helps. Alright, let's continue to move forward. Alright, X-ray. I believe that Professor Lee spent some time to talk about some X-ray sort of application, right? A little bit about science. I just want to check for those in this class that are currently taking XRE classes, so in the past has already gone taking XRE classes. Can you raise your hand? Yeah, can you a little bit higher? So 1, 2, 3, 4, 5. Okay. All right, you can put it down. Thank you. Yeah. So one thing I would say that X-ray is a really robust tool, right? It really provides a lot of information. Now, due again the time limits, I'm going to provide you some fundamental, but I do want to kind of recognize that X-ray could do a lot of, for example, tomography. Is one thing we currently have very interested through X-ray technology. So X-ray, I'm sure you already remember these equations. In your exam, I will not be providing this equation for you. So I'm sure you already remember these, right? So lambda is 1.54 Armstrong. Right? So this is the copper wavefront, right? So normally when we only deal with simple qubit, right? We're not really going in depth. So for those, it's E, H, K, L equals to A, and then H plus A plus L, right? So if we input the equation 1.54, we get 2 sides. All right. Any questions so far? I think this is everybody should know that, right? 有人不知道的 All right. You should be very familiar with it. So there's a few things you can do from XRD. I think XRD is it's not really only limited to doing what the face structure it is. It can actually provide you a lot. First is that it helps you measure so you need to first have a spacing layer. Rows of atoms. We need to also determine the orientation of a single crystal. Right. And find the crystal structure or unknown material, and then you can measure the size, shape, yes, small crystal. Alright, well, that's somewhere what X-ray can do, what you should do for X-ray. Alright?你现在去操作 X-ray 是经过受训就可以进行操作吗？是上完课就可以操作？
要考证照
啊？
要考证照，
考证照谁给你考？
就是好像跟他们的算是那种测试的，
对啊，是哪一位的？是吴怡吗？
没有，好像跟学生考就可以了。
学生考。
对，他们有一个那种像代测的委员。
哦，然后考完就可以那个。
对对对。
Alright, so good. So let's move forward. I think a couple of you. Residual stress. So I think in the past, few instructors or some instructor might have someone mentioned about residual stresses. To clarify, what is the definition of residual stresses? How do you get residual stresses? I want to use this time to clarify that. So residual stresses, 残留应力。 我们是怎么得到残留应力这种东西 ？So first is through plastic deformation, right? So how do we get residual stresses? All right, I'm gonna list it. There's actually only three ways you can get residual stresses. Any other ways you don't get residual stress? So plastic deformation, 是塑性变形 you will get residual stresses. All right. Second is temperature change. Right. Temperature change, you get a structural stress. Temperature change. And the third is structure change. Structure. When I say structural change, meaning jumping off phase transformation. Like for example, iron where you have modern static transformation, right? I believe everybody know. When you change from FCC, BCC, or HCP, something like that, or alpha, 波浪体变肥一肥液变出来流血，看你之类的，是 structural change. Right? So these phase structures also will induce residual stresses. So these are the three common things that you will see. Alright? So, I was thinking maybe I should provide you the X-ray. So, by the way, through X-ray, you are able to detect residual stresses. And I also have the equation here. But, actually, on the second block, I'm not going to write the equation because here's the thing is, when you use X-ray to do residual stresses, you have to be very particularly cautious about because there's other factors that influence. I'm sure that Dr. Lee mentioned that because for say this plastic deformation, temperature change, and structure change, and other things, right, through X-ray. So there's too many factors that kind of overshadow these results. So using X-ray to detect residual stress is a very ambiguous area, still a very ambiguous area. 还是非常混沌的领域啊，所以借由 X-ray 得到产品力，我觉得这个还是可能之一。Good. Any other further questions? If not, let's move on. All right. So heat and thermal transfer. I think this is also important for some of you guys, especially if you're doing heat or transfer. I'm only including this simply because during MIM we involve furnace, right? So heat transfer for all materials is necessary thing you should know. So heat capacity, I already sort of write this down. Capacity is Q equals to MC delta T. Here, when I say C is, again, specific heat capacity. So C, I'm just moving the denominators and the numerators, Q and MC. So it's the ratio of the heat energy Q required to change the temperature of the mass by amount of the heat is called specific heat, right? So Q here stands for heat energy. For those that are doing some heat transfers or heat measurements, this is something you should remember by heart, right? You should remember this. This is your language. I'm not doing this, or I don't remember, but you should remember. You should be more familiar than I am. So you should copy this down as well if you're doing heat or thermal transfer. While you're copying this down, for the final exam, there will be 10 questions, each 10 points. It's a rhetorical question, so meaning that it's not a multiple question, by the way. It's a rhetoric, so you have to write definitions and all this stuff, right? So it's not a multiple questions, right? So, for example, to give you an idea is, I'm going to ask you what is MIM. Please draw the mechanisms, the working functions, and the process, right? So that's worth 10 points. Right? So that's maybe one of the questions I will ask you. Maybe the question I'll ask you, what is XRD? Please provide the equations and what is the definition and how can I use XRD to measure specimens? Please briefly explain what's going on. So that's 10 points. So we have 10 questions for that. Yeah. So it costs you 30 of the total of that, right? By the way, just for your final report, please do not be sloppy. I really read each of everyone's report. 就你们讲的那个报告不要乱讲，我是真的每个字都会看，而且我还会去帮你查对那个剽窃的那个我们学校的被抓到直接给你部分，所以你不要千万不要这种讲述，我是一个字一个字看。Alright, so yeah, so thermal conductivity. I here also listed a few numbers. I really think this is a common knowledge.
So metal is aluminum and copper is a common material used. Polymer called fiber epoxy that you use. Ceramic, alumina, and fused silica SiO2, right? So these are I really believe this is 6 material that we commonly use. And I have taken the token to rank them from the highest to the lowest, right? Well, actually not highest to the lowest, but you can see metal normally has a higher thermal conductivity, right? So it's watt divided by meter times K, okay? So you have roughly 200, right? And polymer is about 0 to 2. Ceramic is about 1 to 40, right? So in the future, if you go measure the material thermal conductivity, right? One would expect 你的心中会想说，你今天去买了这个陶瓷，你心中大概会有个答案说，你这个的导电度 thermal conductivity. Would you go measure? You have an idea, all right? What is a reasonable measurement, right? If you go measure ceramic, you should get like probably 2 or 5, maybe 10. Right? If you go measure metal, it should be 100 or maybe 200. Right? Does that make sense? Okay. It's like that should be the number, right? So how do I, as a material scientist, how do we manipulate to maximize that material performance for thermal conductivity? So the mechanism for heat conduction is K, that's the thermal conductivity, equals to K sub E, K sub L plus K sub E. So K sub L over here is the lattice phonon. So phonon meaning that it's the phonon that is in your material that is constantly vibrating. Plus Ke, meaning that it's the electrons that's also in the material that vibrate. Alright? So I here already organized for you, I think it's also for your benefit to remember, is that if you look over here, metal, ceramic, and polymer, for metals, if you want to increase the thermal conductivity, you can manipulate its electrons inside the material. While in ceramics, you can use phonons for lattice vibration, right? Lattice vibration. And polymer is a vibration rotation of chain molecules inside the material. So these, when you ask me, how do we vibrate electrons inside the materials, right? How do we do that? Well, there's a lot of ways. You can have defects, you can have dopings, maybe other ways you can do that. Using other physical ways, you can do that. But in terms of differences, yes, there is difference. For metals, it's through electronic vibrations, and ceramic is through phonons. So actually, I have no idea what's the definition of phonons. So the definition of phonon, I think the concept is still very ambiguous as well. How do we increase the vibration of phonons is, I think it's very difficult from my current understanding. But anyway, this is to give you some idea. All right? Good? So I also might ask you if this is the final exam.
你还有一些勾品啊，或是不纯，比如说90点99跟91点9，然后你比如说你有做加工，塑性变形才造成的关系，所以我为什么故意给337？我给一个方，就通常它不会有个定值，那定值是除非你今天这个材料你做出来是一个定值。Great question, by the way. By the way, I have also measured ceramic material for thermal conductivity, and every time when I measure the thermal conductivity, it's slightly different. It's never constant, right? There's always a standard deviation, so I mean, that's understandable.
So, is there any way we can differentiate phonon, thermal conductivity and electronic part of it by using some thermal conductivity method? So we can separate it out, like, or
Yeah.
it's always it's giving us a combination of it.
Yeah, I think there's a difference because just judging by its bonding is different, right? Because metal is a metallic bonding, right? Yeah, and through the bonding. Yeah, through its bonding are very different, right? Now, if you want to increase the ceramic conductivity, there's two things you can do. One is currently there's the famous material like MaxFace, right? This is 2D structures and they are very similar, because of the layer structure that make it same. Second is if you do doping, right? You add a sequential like a metallic material inside that increases electric conductivity, something conductivity. Yeah. Does that help to answer your question? Does that?
Actually, my exactly question is about when we do we use light flash method or thermal flash method
Yeah.
to measure the thermal conductivity. At that point, can we differentiate or segregate like this portion of thermal conductivity comes from the phonon scattering and this one is comes from the electrons, free electrons. Is it possible something like
Not
that?
that I'm aware of. Actually, I did that. Yeah, I've done it before. Actually, I was planning to, right? But not that I'm aware of. How do you actually separate? Right? How do you even separate?
Because this is a question I always getting by in meetings with some freshers. Maybe
Yeah,
is it possible to do something like that? Or another thing is like you are working in ceramic, how you know that this portion is coming from the phonon only?
Yeah, that's a great question. I mean, I think the ones that actually also are like they want to solve this kind of question, right? They want to understand. And I'm gonna be honest with you, I don't know. Actually, I really don't know. And maybe this is also entirely wrong, right? The hypothesis about phonon that really plays the role of increasing electric conductivity, maybe it's wrong. Yeah, I really don't know, right? And by the way, it's partially my fault. Is this information? You know where did I get this information from? I actually copied this from Callister, right? Yeah, I didn't really dump this from any advanced textbook. This is from Callister. Yeah, so anyway, so just give you something. Let's continue to move on, okay? So when we talk about thermal conductivity, we might as well talk about electric conductivity since they're proportionally similar. Right?
So again, I give you aluminum, copper, carbon fiber, and oxygen. Right? These are the densities you should be familiar with, and the conductivity. So the resistivity is the inverse of conductivity. All right, so they're inverse. So just put it in put that in 1 divided by 38.2, you get 2.65 times 10 to the power of minus 8. All right, good. So this is the equation to measure the resistivity or the resistance. Again, for those that are doing thermal conductivities for research, I think you should also remember the electric conductivity equation, which is R is the resistance equals to the resistivity times L is the length divided by A is the area, right? Equals to, again, this is zone, is resistivity, L divided by W T. All right. So really, what this is saying, this L is just a different way of writing. Okay. So L is the length, A is the area. So A is W times T. Right. So let me also include that. So this is W, and this is T. All right. So sometimes when you're in the lab, you have an ohm meter, right? You have a conductive meter, right? You get this 2 probe, and then you put it on a material. You measure the resistance, right? So if it's electric conductive, right, it will give you a resistance. All right. That resistance will change because the distance between these 2 probe area change. Does that make sense? That's true, right? Okay? So what is the point of measuring the resistance, right? The point of measuring resistance is that if you put the 2 probe on it, it gives you that number, meaning that yes, it's electroconductive. Now if you put the probe on it, and it doesn't give you any number, meaning that it's an insulator already, all right? So what this means is that the conductivity or the resistivity is an intrinsic property. Just like density, it will not change. All right. However, your resistance do change because the probe, or between these 2 probe distance, change depending on the distance that you put. Right. So, how do we get the resistivity? Actually, resistivity, electricity, is the number that we are more interested in rather than resistance. Right. So the way that we do our measurements is actually quite easy if you know this equation, because what this number is actually saying is R is the resistance you get from the probe, right? Resistivity is an intrinsic property that will never change, okay? And if you somehow change the L, change the A, then you can backtrack and calculate your resistivity if you know your R. Does that make sense? Right? So let's move on. So A over here is W times T, which I already kind of stated. It's the cross-section area. So all the specimens, I'm sure that they have a third of thickness, right? So that's the cross-section area. 破断面就是它的 A 就是它的破断面，它永远不会变嘛。However, the L, the length over here does change depending on where you put the 2 probe. 就是你今天去量它的电阻的话，你今天这个探针，比如这样下来，探针这样下来，或它所量的电阻会完全不一样。比如量这样电阻一定比较大，量这样电阻一定比较小。OK， 那不管是放这样或放这样，它的 A 不会变嘛，它的节电器不会变嘛，因为又没有它的节电器，但是它的 L 会变嘛，这样跟这样会变。那我这样的话。如果 if I know the distance change, right, then I can do a somewhat like this thing, right? We can change the probe distance, right? The probe distance, right? Then we can plot the R with the function of distance, right? So this, if we increase the distance, the R increases, right? So R increases. L increases, we already know the A, we can then calculate the resistivity, which is an intrinsic property. So all the research that you're doing, if you want to measure the resistance, well, if you want to measure the resistivity, it's very easy. All you need is a probe, a very easy cheap probe, and you just have to make sure the resistance change. Measure this distance equally, you mark the distance and backtrack and calculate the resistivity. Mission accomplished. Very easy piece of cake, right? So there is some very expensive commercial equipment, 非常贵重的仪器 that they show you, they tell you this is a 4-point probe, just the antenna out. What they tell you is that when you put the probe down, the algorithm, the system, automatically give you the resistivity. Right? Only the equation is just this equation, right? You don't need a freaking resistivity machine to measure. 那个4点探针的，你就直接回去拿一个 very cheap probe and then measure visual distance and measure the calculate resistivity. Alright?
Does it make sense? 有没有其他问题？没有的话，我看一下。Alright, so this is the last slide I want to share. These are the most important slide. I think you should really copy this and I'll take a photo. So today, or not today, in a couple few weeks we will have an exam, right? So these are the questions, 10 questions, alright? I'm going to be, hey, if you fail this exam, it's not my problem, it's your problem, okay? Alright, just to be very clear. And by the way, is that the review report, if you really feel that, it's not my problem, it's your problem, okay? 就我知道真的讲就是这个东西你都可以 fail，那是你家的事，不是我家的事，我已经跟你讲。So I'm really again very straightforward. There's only a difference between me telling you what exactly the question is, right? So the first question, what I'm going to ask you is explain what is stereolithography is, right? What exactly is this stuff, right? Give me an example of 3D printing, all right? 就是除了 stereolithography 有没有其他 3D what's the other example? 2 examples, by the way. Second is what is XRD? What is residual stress? Right? I think I already covered that, right? We talked about that, right? Third is what is injection molding? Explain what injection molding is. What are the process of injection molding? What is the mechanism of injection molding? These are legit questions, by the way. The instructor have talked about this, give you video again and again. Sometimes I feel it's already enough, right? So you should be able to explain. Fourth is the cold spray. I think at the beginning of the second or third class, I talked about what is cold spray. So tell me what is cold spray is. By the way, I'm an expert in cold spray, so I think for you guys should also know what cold spray is. Give other example. What's the cold spray family? Yeah, cold spray. So what family it is in? So it's in thermal spray. So in thermal spray, there's not only cold spray, but there's other spray. Right. So 5 is whiteboard statistic. What is whiteboard statistic? Right. Second is Moldex 3D. What's the importance of using Moldex 3D? What can Moldex 3D provide? What is the step for using Moldex 3D? 7 is powder atomizer. I talked about this today at the beginning of class, powder atomizer. So explain what is powder atomizer, what are the steps, and what is the mechanism and stuff. 8 is bending. Exactly what the question is, I don't recall, but what are these equations for? What does it do? How do you derive these equations? I haven't derived these equations today, but I think it's your job to go find out. 9 is polymer science, so I talk about a little bit polymer science between thermoplastic and thermoset. These are, again, very fundamental knowledge you should be aware of. And 10 is thermoelectric conductivity, right? So these are combined things about the equations, how do you derive these equations, and what are these definitions. So in these tests, is again a closed book. You should remember all of these, in your brain, by the way. All right. Questions so far? You guys have any questions? All right. So if we don't, I will see you. You know what I see you. So I won't see you next week, but I will see you in week 15. So Dr. Chi will come and talk about powder analysis, and that's the own paper due, and on week 16 in the final exam. Right? So you have approximately, oh my God, we have like 3 weeks to prepare, more than 4 weeks to prepare your final exam. Right? You can't really complain that, right? They give you what exactly you need, right? Right? This is really very easy stuff. I can't fail this, right? Everybody should get 90, right? Anything below 90 should come and beg me to my office.